your do now sheets, having the notes packet out will be useful as well. What we're going to do for the do now is review some things with conjugate acids and bases and looking at the strength. And then on the side counter is a pink sheet. It's Appendix D. You don't need it for today, but you will need it once we start getting into weak acids and weak bases. So I just had it copied. I figured you can pick it up now. You can put it in your binder now so that you have it. Today we're going to be going through different examples, not necessarily in order. So we're doing 10, 11, and 12, which is reviewing some things from yesterday. Example 4, and then 6 through 9. So we're kind of doing some different examples today, but every single example that we are doing corresponds to a mastering question. So every single example today is going to have a mastering question that's going to go along with it. So we'll just get into the do now, and then hopefully have at least a little bit of time at the end that you can work on mastering, so you can kind of take the examples that we do and work on mastering. So 1, 2, and 3 are asking about the conjugate base for these acids. 4 and 5 are asking about the conjugate acids of these bases. So for 1, 2, and 3, the conjugate base, remember that the base will have one less proton, one less H+. The conjugate acid will have one more H+. So when you're looking at the base, remember the base should have one less hydrogen. So for 1, 2, and 3, we're removing an H+, because the conjugate base is what you get when you remove an H+. So the only H in number 1 is at the beginning. So when we remove the H, it becomes ClO4. But not only are you removing an H, you're removing a +1. Right now, HClO4 is neutral. If you're removing a +1, you're also removing 1 from the charge. For number 2, the only place where we have hydrogens are at the end here. So we're removing one of them. An acid-base pair only differs by a single proton. So we're removing one of the hydrogens, so it's pH3, and we're removing a +1. So right now it's +1. We remove that +1. It's not going to have a charge. And then for number 3, the only, what we would say, ionizable proton, the H+ that you can remove, is at the beginning. So we're going to remove this H. It's going to become CO3. And you're removing 1 from the charge. So instead of -1, it would be -2 or 2-. Now for 4 and 5, this one's the conjugate acid. So the acid always has one extra H. Typically you're going to put it at the beginning unless you know that it's organic, which we looked at some examples of yesterday. We'll continue to look at examples like that. So for number 4, it's Cn-. You're adding 1 H+. So you're adding an H to the beginning, so HCN, but then you're adding a +1. So if it's -1 and you're adding 1, it becomes neutral. Number 5, you're adding an H, so we'll add it to the beginning and add 1 to the charge. So instead of 2-, it's just going to be -. So notice how for 1 through 5, every single one of these pairs only differs by a single proton. The acid always has the extra proton, the base has one less proton. And then for number 6, the conjugate base of a strong acid. So let's say we're looking at something like HCl. The conjugate base of HCl, so the base has one less proton, that's Cl-. Yesterday we talked about the pair that we can have. You can have one of 2 pairs. You can have strong neutral or weak and weak. So if this is a strong acid, its conjugate base is neutral. So when you have a strong acid, its conjugate base is neutral. Same would go if it's a strong base. Its conjugate acid would be neutral. Okay, so that's it for the do now, just reviewing the conjugate acid-base pairs. We'll look at this a little bit more as we go through some examples for today. I do want to put this up, so while you're getting your notes out, if you don't have your notes out already, I put this table together This is in the Do Now slides, and I'll have this table up quite a few times, but this is showing the alignment between the mastering questions and the example questions. So if you want to take a picture of this, you can, but you'll see that there's the mastering questions and then the example number that goes along with it. So if you're working through mastering, and let's say that you get to question, 26, and you're stuck on question 26, make sure you look at this, because if we haven't done example 14 yet, then just wait until we go through that example, because a lot of the examples that we're doing will align with a certain mastering question. And I'll continue to put this up whenever you have work time on mastering, just so that you can go back and reference your examples as needed. So again, this is just how the questions in mastering are aligning to our examples. After today, you can go through, I want to say number 19 of mastering, so you'll be able to get a decent amount done. So what we're actually going to do is we're going to skip ahead to example 10. So if you go in your notes, I believe page 17 is where you'll find example 10. So examples 10, 11, and 12 we're going to do first, because this is reviewing topics from the first video. This is looking at, is something strong or weak? What does that mean about its conjugate? And this goes along with some of the mastering questions that you may have seen yesterday. So this is similar to number 6 of mastering. So if you want to make notes in your examples as well, this is similar to number 6 of mastering. And so for this example, it says label each of the following as being a strong acid, a weak acid, or a species with negligible acidity. So when it says negligible acidity, negligible means insignificant. Or we always would say it's neutral. So negligible acidity means that it's not acidic, right? So we could think about it as being a neutral substance. So these are all acids, right? It tells us strong acid, weak acid, or insignificant acidity. And then in each case, write the formula of its conjugate base and indicate whether the conjugate base is strong, weak, or neutral. So we'll go through each one of these, and we'll kind of just answer the questions directly underneath. So I'll kind of just do part A, and then part B, and part C, and so on. So for this question, first thing, know your strong acids. Know your 7 strong acids, because if it's one of your 7 strong acids, then you know that it's strong. So if I look at these 5 options. One of them is one of the 7 strong acids. H2SO4 is one of the strong acids. So we know that that's a strong acid. So if it's asking, which one is stronger, well, if it's one of the strong acids, that's going to be stronger. And then what we can do is we can kind of look through, and I'll give you a hint for some of these, because when you're like, how do I know if something is neutral? It might get a little bit difficult. But for 7, CH4 is methane. Methane is the gas that comes out of the gas jets. Well, we know from yesterday that acids react with metal. So if methane were acidic, whether strong or weak, if it were acidic, it would react with the metal pipes, with the gas jets. We know that that doesn't happen. So CH4 is actually neutral, or it's a substance with negligible acidity. That is the only neutral substance on here. Typically, we're going to focus on strong acids and weak acids. Right? If it's not one of the 7 strong acids, we're going to say it's weak. So for A, this is a weak acid. Pay attention, right? This is HNO2. HNO3 is a strong acid, but HNO2 is not. This is a weak acid, and this is a weak acid. Now, as we go through, we're going to talk about ionizable protons. That's the H that we can remove. So in A, the H that we can remove, the only H is at the beginning. In B, the only H, well, the only H's, right, are at the beginning. Same with C. D, if there were any ionizable protons, it would have to be one of these. And then E is where we notice that there's H's in two places. Yesterday we talked about how the H that gets removed is the one that is attached to the more electronegative atom. Nitrogen is more electronegative. And so that means that nitrogen will pull the electrons toward it, making it easier for the H to be removed. That's considered an organic acid because it comes from a base. So we've gone through and we've labeled. We've labeled the acids, whether they're weak, strong, or neutral. Now, something to keep in mind, I'll just write it over here, is comparing the acids to the bases. Remember, you have really one of two pairs you're looking at, strong and neutral or weak and weak. If you have a strong acid, its conjugate is neutral, right, or has negligible acidity. If it's a weak acid, its conjugate base is also weak. The third option is if we have a substance that has negligible acidity or is neutral in terms of the acidity, its conjugate will be strong. So notice how we always have one of two pairs, strong and neutral or weak and weak. So as we go through and we look at the conjugate bases, we can use this to figure out, is the base strong, weak, or neutral? So see if you can go through A through E and write the formula for the conjugate base. See if you can go through each one of these and write the formula for the conjugate base. Remember, conjugate base has one less proton. So see if you can go through. I'll go through as well right underneath so you can check. But see if you can write the formula. Just practice with the conjugates. Remember, you're only removing one proton. So for part B, you're only removing one of the protons. Acid-base pair only differs by one proton. So you're removing not only an H, but because it's a proton, it's H+, you're removing a +1 as well. So you can go through, right, double check, make sure you've removed an H and a +1. You're not changing any other part of the formula. All you're doing is removing an H+. And then the last thing is labeling the conjugate. So labeling the conjugate is based on the type of acid that it comes from. So NO2- comes from a weak acid, which means its conjugate base will also be weak. So you'll see me label like WA for weak acid and WB for weak base. Part B, H2SO4 is a strong acid. So if it's a strong acid, its conjugate is neutral, has negligible acidity. C was a weak acid, which means its conjugate base is a weak base. Now part D, methane, was neutral in terms of its acidity. You still can only have one of two pairs, strong and neutral or weak and weak. So if this is neutral, that means that this is actually a strong base. And then for E, came from a weak acid, so this is a weak base. So this allowed us to go through and to look at if something is strong, weak, or neutral. In the notes, there's that chart as well. I believe the chart was on page 3 that showed, the acids and the bases. And so for some things like CH4, you could look on here for the acidity. But otherwise, I would give you a list of strong acids and weak acids. And then you just have to pick. The 7 strong acids. If it's not one of those, we're going to assume that it's weak. So make sure that you know these pairs, right? You have one of two pairs, strong and neutral or weak and weak. And again, that's like number 6 of mastering. Questions on this example? So example 11 is another mastering question, and this is very similar to the mastering question. This is like mastering number 7. So this is like number 7 of mastering. This has 2 parts. So we're looking at which one is the stronger acid and then which one is the stronger base. So again, we're looking at the strength of an acid and a base and what that means about conjugates. So if we take a look at part A, which of the following is the stronger acid? Now notice how for A and B it says briefly explain your choices. So we want to just give some sort of quick explanation. So for part A, which one of the following is the stronger acid, HBRO or HBr? Now you're looking at this and you're like, okay, like how would I know between the two? Well, always look for one of the 7 strong acids. If it's one of the 7 strong acids, it's going to be stronger. HBr is one of the 7 strong acids. So I'm just going to say 1 of 7 strong. HBr is one of the 7 strong acids, and so that's going to be the stronger of the 2. Now part B says, which is the stronger base, F minus or Cl minus? Now when you're looking at the strength of the base, these are conjugate bases. Right? These are the results of an acid losing its proton. So what we can do is we can look at the acid that both of these came from. So look at the acid that both of these conjugate bases came from. F minus comes from HF. Cl minus comes from HCl. If we know information about the acid, we can determine information about the base. So if we know the acid, we can look and say, okay, well, is this a strong or is this a weak acid? Well, we know that HCl is one of the 7 strong acids. If HCl is a strong acid, what would that mean about its conjugate base? It's neutral. HF, I put HF on here because year after year people make the same mistake. HF is a weak acid. If HF is a weak acid, what does that mean about its conjugate base? Remember, you have one of 2 pairs, strong neutral or weak and weak. So since HF is a weak acid, that means that F minus is a weak base. So this is what we're comparing. A weak base versus a neutral substance. One of them is still a base. Even though it's weak, one of them is still a base. A neutral substance has negligible basicity, meaning it's not basic. And so if we want to look at this, right, F minus is a weak base, Cl minus has negligible basicity or is neutral. So which is the stronger base here? F minus. Right, and so if we wanted to look at this, we can say F minus is the conjugate base of a weak acid, meaning it's a weak base. Cl minus is neutral. A neutral substance is not basic. A neutral substance is not acidic. So again, this will help you. I believe this is a multiple choice question on mastering. Number 7 of mastering looks at this. Okay, so then we're going to look at example 12. This is the last kind of review conceptual example from yesterday. So I want to look at this again because I want to hit this a few times when we're looking at equilibrium. So in every acid-base reaction, so remember, an acid-base reaction deals with transferring protons. In every acid-base reaction, equilibrium favors transferring the proton from the stronger acid to the stronger base. That means that the stronger acid and the stronger base act as the reactants. And so the reaction will shift accordingly. Maybe that means your forward reaction occurs, maybe that means that the reverse reaction occurs, but the stronger acid and stronger base must be the reactants. And And so what we have to do is we have to compare the base on the left of the arrow, right, or the acid, and the base on the right of the arrow, again, or the acid. The stronger ones must act as the reactants. In this example, acetate is a stronger base than H2O. And if you say, how do I know that? We can utilize that chart on page 3 of the notes. And we'll use that chart for example 12. But since acetate is a stronger base, these act as the reactants. That means that H3O plus is transferring its proton. These act as the reactants, so the reverse reaction occurs. So we would say equilibrium lies to the left. The arrow would point to the left. These act as the reactants. These act as the products. But it's always about what's your stronger acid and base. So example 12, this is like number 9 of mastering. So this is like number 9. Again, I think it's very similar to the question of mastering. So predict the products of the following acid-base reactions and then determine whether equilibrium lies to the right or the left. So for part A, the first thing we need to do is predict the products. Now it tells us it's an acid-base reaction, which means we know that there's a transfer of an H+. That's the definition of an acid-base reaction, transferring a proton between an acid and a base. Now if we look at part A, only one of the reactants has an H that it could donate. O2 minus, the oxide ion, doesn't have an H. It can't donate anything. That means that water is going to donate one of its protons to the oxide ion, which means water, if it's donating, is the acid. The oxide ion, if it's accepting, is the base. Now, based on this, we can write our products. Once O2 minus accepts an H+, we have OH, add 1 to the charge, so OH minus. Once water donates its proton, it loses an H+, it becomes OH minus. Now, on this side, we're going to label, it doesn't really matter which one we label because it's the same thing, but the way that I wrote it, I said, when oxide gains its proton, it becomes the conjugate acid. When water donates its proton and acts as the acid, on the other side of the arrow, once it loses that proton, it becomes the conjugate base. Now, there's our products. We have OH and OH. Now, this is where the chart on page 3 of the notes will be useful, only because, oh, I'll put it right here. Okay, right, here's the chart that's on page 3 of the notes. The reason this is going to be useful for part A is because you don't have to memorize this. I'm going to show you in part B how we can do it without the chart. But for part A, you don't have to memorize all of these. And so what we're doing, I'm going to compare the bases. You could do the same thing with the acid. I'm going to compare the bases. So I'm going to compare O2 minus and OH minus. I'm going to compare oxide and hydroxide. On this chart, notice that base strength increases as you go down. So I'm comparing O2 minus and OH minus. They're right next to each other. But O2 minus is farther down. O2 minus is the stronger base. Equilibrium favors the stronger base accepting the proton. That means that O2 minus and H2O, these will act as the reactants, forming the product. So my arrow, notice how my arrow is pointing from left to right. The forward reaction is proceeding. Because notice how it's at equilibrium. So the forward reaction proceeds. When we talk about equilibrium lying to the left or the right, it's which way is the arrow pointing? If the forward reaction proceeds, that means it goes from left to right. That means that equilibrium lies to the right. Equilibrium lies to the right. That means we're creating products. So just to review, if we're creating more products, K is greater than 1. So since we're creating more products, K is greater than 1. So again, equilibrium favors the stronger base, accepting the proton and acting as the reactants. Now we look at part B. Let's look at part B now. Again, we know it's acid-base because they tell us, so there has to be a transfer of a proton. NO3 minus does not have a proton to donate. So that means that, again, water has to be the one to donate the proton. Water acts as the acid, NO3 minus acts as the base. So now we can write our products. When NO3 minus accepts a proton, it's adding an H plus. It becomes HNO3. When the base accepts a proton, it becomes the conjugate acid. Once water donates its proton, it becomes OH minus. Once the acid loses a proton, it becomes the conjugate base. Now, when we look at this, again, we want to determine whether equilibrium lies to the left or to the right. So we have to compare. You can pick. You can compare the acids or the bases. I'm just going to compare the bases. Now, here's how we can do this without this chart. Now, you have the chart so you can double check. But NO3 minus comes from HNO3. HNO3 is a strong acid. If HNO3 is a strong acid, what does that mean about NO3 minus as a base? It's neutral. We know that hydroxide is basic because we've been looking at strong bases having hydroxide. So we know that hydroxide is basic. It doesn't matter if it's strong or weak because NO3 minus is neutral. So what this means is that hydroxide is the stronger base. Now you could look at this chart and make sure, right? You could look at this chart and double check. You find that OH minus down here is stronger than NO3 minus near the top. Now make sure you pay attention. Acids increase up, bases increase down, because that's what happens with the strength. The stronger the acid, the weaker the base. Vice versa as well. So since OH minus is the stronger base, that means that these are going to act as reactants. So I'll put act as reactants, which means the reverse reaction proceeds. Right? Reverse reaction proceeds. The arrow points to the left. So equilibrium lies to the left. That means you're creating more reactants. You're using up products, making more reactants. That means that K is less than 1. Remember, when K is less than 1, that means reactants are favored. And so again, this will help you with mastering. Number 9, you have to actually write the products and then predict which way equilibrium will lie. Any questions on this one? No? All right, so now we're going to kind of shift to the math. And just a reminder, so this table is on page 5 of the notes. You had to fill in this table that looks at if something is acidic, basic, or neutral. Now, I just want to remind you that these values are assuming 25 degrees Celsius. Yesterday, we talked about the definition of a neutral substance. The definition of a neutral substance is not based on the pH. We're going to be talking about pH today. A neutral substance is not based on a pH of 7. That's only at 25 degrees. The definition of a neutral substance is when H plus and OH minus are equal. If one is greater than the other, that's going to make it acidic or basic. Right? H plus tells us how acidic something is. The more H plus, the more acidic. OH minus tells us how basic. The more OH minus, the more basic. If they're equal, that's neutral. Now, again, know your 7 strong acids, know your strong bases. I wanted to put this on. I know some people were drawing this on their periodic table yesterday. So remember, anything lithium down and then calcium down makes that lowercase b on the periodic table. Any of these with hydroxide. So like LiOH, CaOH2, KOH, SrOH2, those are strong. If it's not one of these bases with hydroxide, not one of these metals with hydroxide, it's not strong. Just like if it's not one of the 7 strong acids, it's not strong. That's going to help us as we're going through some of our pH calculations today. So again, when we're classifying as acidic, basic, or neutral, we're just looking at, do we have more H plus, do we have more OH minus, or are they equal? So we'll kind of keep that in mind. We are going to look at KW again as well. So in both videos, 7.1 and 7.2, we talked about KW. KW is on your equation sheet. All right, on your equation sheet under equilibrium, you have KW equals H plus times OH minus, which is 1 times 10 to the negative 14 at 25 degrees Celsius. At 25 degrees Celsius is the most important part of that. If we are not at 25, KW is nothing more than an equilibrium constant. We know that equilibrium constants change as temperature changes. So as temperature increases, we actually see that KW increases. So notice how we go from an exponent of negative 15 to negative 14. So KW actually increases. And so based on that, right, as temperature increases, that means that the reaction is shifting to create more products, which tells us that this autoionization of water is actually endothermic. Right, if it were exothermic, we would notice the other way. But as temperature changes, KW changes. Now the relationship, KW being H plus times OH minus, that doesn't change. But the constant that we use changes as temperature changes. And so it's going to be important that we pay attention to the value of KW that they give us, because that's going to affect our H plus and our OH minus concentration. And so what we're going to do is we're going to actually finish up example 4. Yesterday we did part A of example 4. Today we're going to do parts B and C, because again, this will help us as we go through mastering. And so for this example, again, we're calculating the values of H plus and OH minus. But now it says in a neutral solution at 40 degrees Celsius. The relationship between H plus and OH minus doesn't ever change. Well, I guess I'm going to do OH minus first. Right, KW equals H plus times OH minus. If we were at 25 degrees Celsius, which is what part A looked at yesterday, we can use 1 times 10 to the negative 14 for KW. However, we're at 40 degrees Celsius. They would give us the value of KW. So at 40 degrees Celsius, KW is 2.92 times 10 to the negative 14. KW is 2.92 times 10 to the negative 14. They would give us the value of KW. You do not have to memorize what all the different values of KW are. But it's important to recognize that at a different temperature, KW is different. And so for this, neutral, keyword here, means that H plus equals OH minus. H plus equals OH minus. So if I put in X for H plus, that means that OH minus is X as well. I'm just going to use the KW expression. At 40 degrees Celsius, KW is 2.92 times 10 to the negative 14. H plus is X. OH minus is X. X times X is X squared. And so to solve this, again, this isn't one that you'd be required to do without your calculator just because of the number in front. But you take the square root of 2.92 times 10 to the negative 14th. We get 1.71 times 10 to the negative 7th. Notice how that is different from what we calculated in part A. Part A, we just had 1 times 10 to the negative 7th. Now again, I'm going to put my unit of molarity because this is concentration. Here's my answer for part B. A neutral solution, the definition of a neutral solution is when H plus and OH minus are equal. And so we can use KW to solve that. Now this says what happens to the pH of pure water as the temperature increases. So we haven't quite gotten to, more into pH, but the pH is the negative log of H plus. I went through that in the video. pH is the negative log of the H plus concentration. We're looking at powers now. So pH for the power of hydrogen. What we could do is we could actually just plug this in. Let's plug in at 40 degrees. Let's take the negative log of 1.71 times 10 to the negative 7th. Negative log of 1.71 times 10 to the negative 7th. That's 6.77 at 40 degrees. The pH of a neutral solution at 25 degrees, that's what we're used to hearing. The pH at 25 degrees is 7. So as we're increasing temperature, we go from 25 to 40, what's happening to the value of pH? It's going down. So pH decreases as temperature increases. Here is our answer for part C. As you're increasing the temperature, if we were to increase the temperature in here, or you wanted to find the pH of water, which for us should be neutral, as you increase temperature, pH is going down. Okay, so that's answering example 4. Right, that'll help with some of the questions on mastering as well. And then the last one we'll go through pretty quickly just before we get into the new pH examples. This is, I wrote this down. This will help with number 11 of mastering. So this is similar to what we looked at yesterday. Right, calculate the H plus concentration for each of the following. I know that part B has a question that's almost identical. I think it might be identical in question 11. So for A, they give you the OH minus concentration. They want us to calculate H plus. We know the relationship. KW is H plus times OH minus. When you are solving for one of these concentrations, use KW. Now we're assuming 25 degrees Celsius unless they tell us something else. The reason that's important is because KW is 1 times 10 to the negative 14. 0.0007 is OH minus. So we plug that in. 1 E negative 14 divided by 0.0007. H plus 1.4 times 10 to the negative 11. There's H plus. Compare it to OH minus. Here's H plus. Here's OH minus. Which one's a bigger number? Right, 0.0007. That exponent would be to the negative 4. Keep looking at example 6. Part B of example 6 is a question identical to mastering. So part B says a solution where the concentration of OH minus is 100 times greater than H plus. So they don't really give us any actual values. But if I say that H plus is X, they tell me that the concentration of OH minus is 100 times greater than H plus. So OH minus would be 100 times X. Now we know the relationship between H plus and OH minus. It's always based on Kw, and because we're assuming 25 degrees Celsius, unless they tell us otherwise, we're going to go ahead and use 1 times 10 to the negative 14th is H plus times OH minus. H plus is X. OH minus is 100X. Now be careful with this math. All right, be careful with this math. Can we do this without a calculator? Yes. I'm just going to save some time. So we're going to start by dividing both sides by 100, because that gets rid of that 100. So 1e to the negative 14 divided by 100 is 1 times 10 to the negative 16. What is x times x? X squared. So now we can take the square root. X is 1 times 10 to the negative 8th. Again, if you go back and compare, we want to calculate H plus. X is H plus. So here's the first part of my answer, 1 times 10 to the negative 8th. Now, you could go in and solve for OH minus if you want, but if it tells us that OH is greater than H, the more OH minus, the more basic. So this is a basic solution. Because again, they tell us that OH is greater than H plus. If OH is greater than H plus, it's a basic solution. And so this is how you can go through and solve number 11 of mastering. This is just one part of number 11, but just to help you if you're not given values. Okay, so now what we're going to do is we're going to go in and we're going to talk a little bit about pH. So in the notes, right, in the video, it showed you this pH loop. This is how you can go between solving for different variables. H plus, OH minus, pH, pOH is this loop. Now, down here you'll notice it says the blue ones are on your equation sheet. Now, you still need to know these. You need to know how to go backwards. Inverse log is 10 to the power. So if you want to go backwards here, you multiply the negative 1 over, and to get rid of log, you use 10 to the power. Kind of like ln, the opposite was e. If you look in your calculator, second log is 10 to the x. That's how we can undo a logarithm. So all of these in blue are on your equation sheet. However, these two that are not are still important. You have to be able to go backwards. And so this shows you that there are different ways. If you want to go from H plus to pOH, there are two different ways you could go. They are both correct. I might do an example differently than you're doing it in your notes. If you're getting the same thing, that's fine. So just know that there are different ways that we can go through and that we can calculate. pH means you're taking the negative log of H. pOH means you're taking the negative log of OH. You have to pay attention to what you're working with. You cannot take the negative log of OH and say, there's pH. That's pOH, and then you have to do something else to get to pH. And we'll look at going through these different calculations. Now we're going to talk more about this as we go through and as we practice multiple choice questions. But just to kind of show you for now, first, sig figs with pH is based on decimal places. So if you want 3 significant figures in your answer, that actually means you're going to be giving 3 decimal places for pH. When you want to estimate for multiple choice questions, when you take the negative log of something that has a 1 in front of the times 10 to the power, your pH, right, your negative log is actually just the exponent. All right, so pH is actually the absolute value of your power or your exponent. That's if there's a 1 in front. We'll go back through and review this as we go through and practice. If it's not a 1 in front, you're actually just going to subtract 1 from the exponent. So 8.45 times 10 to the negative 10, we know it's going to be 9 point something for the pH. We'll go back. I'll have this slide up. You'll see this slide quite a few times as we go through and practice. So example 7. So now we're going to get into calculating pH. Example 7 is like number 14 of mastering. All right, number 14 of mastering. So this says if NaOH is added to water, how does the H plus concentration change, and how does the pH change? So if NaOH is added to water, how does H plus change and how does pH change? NaOH is a strong base. I'm going to just write down what I know about H plus and OH minus. I know that Kw relates H plus and OH minus concentrations. This is a strong base, which means when we put this into water, it's breaking apart into its ions. When we put NaOH into water, we are increasing the OH minus concentration. Kw is a constant. So math says, if we are increasing the OH minus concentration, what has to happen to H plus to keep Kw a constant? It has to decrease. In order to keep this a constant, H plus has to decrease. So we actually just answered part A, right? How does the H plus concentration change? H plus concentration decreases. And then it says, how does the pH change? This is where it's important that we remember that pH is a scale that tells us how acidic or basic something is. 0 to 7 is acidic. 7 to 14 is basic. This is at 25 degrees Celsius. If it's not at 25, that scale changes a little bit because Kw is no longer 1 times 10 to the negative 14. So, as you are adding a base, what is happening to the solution, just in general, if you're adding a base? Is it becoming more acidic or more basic? More basic. Right, so as NaOH is added, the solution becomes more basic. You're adding a base, it's becoming basic. Based on the pH scale, if it's becoming more basic, the pH will increase. As a solution becomes more basic, the pH will increase. Only use pH to determine if something is acidic or basic. Only pH. Now you can compare H plus and OH minus if you have those values like we have been, but if you're given values of pH or pOH, only use pH. Now for part B, if H plus concentration is 0.005 molar, what is the pH of the solution? Is it acidic or basic? So let's go through part B. pH. We have a couple different ways that we can calculate pH. We can use pOH or we can use H plus. On your equation sheet, you're going to notice that you have pH equals negative log of H plus and 14 equals pH plus pOH. Look at what you're given. I'm given H plus here. So I'm going to use negative log of the H plus concentration. So to calculate pH, I'm going to do negative log of 0.005. When you do negative log in your calculator, that's already base 10. So in your calculator, you'll just do negative log 0.005. So technically 1 sig fig means 1 decimal. 2.3. Now for part C, oh, nope, this is the rest of part B. Is it acidic or basic? So you're just looking at your value of pH. This value of pH is between 0 and 7. If it's between 0 and 7, it's acidic. Now part C. Part C is going backwards. If the pH is 6.3, what are the concentrations of H plus and OH minus in the solution? Now we are solving for the concentration of H plus. Going backwards is not on the equation sheet, but you need to know this calculation. I bring the negative over, and I use 10 to the x. So it looks like this, 10 to the negative pH. On your calculator, when you hit second log, it does 10 to the x for you. So H plus is 10 to the negative 6.3. So in your calculator, you hit second log, negative 6.3 gives you your answer. Make sure that you can put this in your calculator. 5.01 times 10 to the negative 7th. Please don't forget units. Molar. Now that's H plus. It also wants OH minus. So for OH minus, we have H plus. We can find OH minus. All right, we assume 25 degrees Celsius. We know the relationship between the two. 1 times 10 to the negative 14 is H plus times OH minus. So we can plug in. 1 times 10 to the negative 14 is 5.01 times 10 to the negative 7th times OH minus. So 1 e negative 14 divided by 5.01 e negative 7. The OH minus concentration, when we round, 2.00 times 10 to the negative 8th molar. So there's our two answers, H plus, OH minus. Now there are two ways that you could identify whether this is acidic or basic. The first is based on the pH. The second is by comparing H plus to OH minus like we did before. Based on the pH, it's under 7, we would say this is acidic. And I know that the question isn't asking, but I'm just showing you that there's multiple ways. We would say it's acidic because it's less than 7. We could also compare H plus to OH minus. I notice that the H plus exponent is negative 7. OH minus is negative 8. Negative 7 is a larger number, so there's actually slightly more H plus. It's acidic. So this is looking at just general calculations for pH, H plus, OH minus. If I wanted pOH, right, that P means take the negative log. pOH, I could take the negative log of OH minus to get pOH. Or I could subtract 6.3 from 14. Multiple ways to find it. So now example 8. Example 8 is having us look at strong acid solutions. So example 8 is like number 17 of mastering. Number 17 of mastering. So they're telling us in this, they're strong acid solutions. So strong acid solutions mean that they dissociate completely when put in water. Makes our calculations much, much easier. We're going to look at what happens if they're not in strong solutions tomorrow. So calculate the pH. Our goal for each of these is to calculate the pH of strong acid solutions. Make sure you know your strong acids. Now here they're telling us that each of these are strong acids. But if they don't, you want to make sure that you know those strong acids. So for part A, 1.8 times 10 to the negative 4th molar HBr. Now you're going to need space for this, so try to like split into like 4 parts maybe. Just keep in mind that there's 4 parts to this example. So part A has us looking at HBr. Now I'm going to start by just writing what happens when I have HBr in solution. It is a strong acid. It completely ionizes into H plus and Br minus. Now the reason I'm writing this is because I'm showing that if I have 1.8 times 10 to the negative 4th molar of HBr, if it completely ionizes, that means I'm also going to have 1.8 times 10 to the negative 4th molar of H plus and 1.8 times 10 to the negative 4th molar of Br minus. Right? All of the HBr ionizes. So I notice here that the concentration of HBr equals the concentration of H plus. This is important because that's what happens when we have a strong acid. This is a 1-to-1, 1 acid, 1 H plus. So if they give us the concentration, we just start saying, okay, strong acid, H plus concentration is the same as that strong acid. Which means, here's my concentration of H plus, right here. My goal is to calculate the pH. pH is negative log of H plus. So again, that P means take the negative log of 1.8 times 10 to the negative 4th. So you practice putting it in your calculator. Negative log, 1.8, E negative 4. 2 sig figs means 2 decimal places. So 3.74. There's our pH. That's a nice one. All right, the concentration of the acid is equal to the H plus concentration. Now part B, we have 1.02 grams of HNO3 and 250 milliliters of solution. Well, I know that to calculate the pH, I need to know the concentration of the acid. So need to know concentration of HNO3 before we can calculate pH. Concentration is molarity. Molarity is moles over liters. So part B is requiring us to do some stoichiometry. We have 1.02 grams of HNO3. I need moles. The 1.008 plus 14.01 plus 48, 63.018 is the molar mass. grams per every 1 mole. Again, I needed to find the molar mass because my goal is to get the concentration. To find pH, I always need molarity. 1.02 divided by the molar mass. Be careful with rounding. I'm going to keep this in my calculator. If you round to 2 sig figs, mastering will probably count it wrong. Keep it out to 3 or 4 sig figs. So 0.0162 moles, 250 milliliters is 0.250 liters. So I divide my moles by 0.25, 0.0647 molar. Here's the concentration of HNO3, which is also the concentration of H plus because it's a strong acid. When it's a strong acid and it's 1-to-1, like HBr has 1H, HNO3 has 1H, the molarities are equal. Now I can find the pH. pH is negative log of the H plus concentration, 0.0647. I'm going to just leave everything. I always just leave it in my calculator. I'm going to just do 3 sig figs. I'll do 3 decimal places here. 1, 8, 9. Now I want you to notice both of these values of pH. Notice how they're well below 7 because they're strong acids. So these are well below 7. Now let's look at part C. Part C says we have 2 milliliters of 0.5 molar HClO4 diluted to 50 milliliters. Key word right here, diluted. What's the dilution formula? M1V1 equals M2V2. This is an equation not on the equation sheet that you also need to know. We have a few like equations that you need to know. This is one of them. Diluted is the key word. So M1, 0.5 molar, V1, 2 milliliters. Now remember, as long as your units are the same, you don't have to worry about converting volume. Let's solve for the new molarity when the new volume is 50 milliliters. So again, because it's diluted, we need to figure out the molarity before we can calculate the pH. So divide 50 over. M2 is 0.02 molar. Now that's the new concentration of HClO4, but because it's a strong acid, that's also the concentration of H+. So to find the pH, we'll just take the negative log of 0.02. And let's do, 3 sig figs. We'll do 3 decimal places. I'll just do it down here. pH is 1.699. So part C was a dilution. So each one of these are just different ways of finding new concentrations. Now part D, so the last one. Always save best for last. This says a solution is formed by mixing 10 milliliters of 0.01 molar HBr with 20 milliliters of 0.25 or 2.5 times 10 to the negative third molar HCl. We're mixing 2 strong acids together. So when you mix 2 solutions together, you need to determine the number of moles coming from each acid and then the volume. So the new molarity To calculate the new molarity, you need moles coming from HBr plus moles coming from HCl divided by the new volume. Now remember that new volume needs to be in liters. Well, let's start with the volume part. That might be easier. 10 plus 20 is what? 30. All right, so the new volume is 30 milliliters. Put it in liters. 123.030 liters. The new volume is just adding the two together. Now, to get the moles, we just need to figure out how many moles are coming from HBr, how many moles are coming from HCl. So I'm going to use the molarity formula for both of these. So we'll do HBr and HCl. Remember, molarity is moles over liters. Please make sure that you're checking your units. So, molarity of HBr is 0.01. I'm trying to figure out how many moles of HBr do we have if we have 10 milliliters. 1, 2, 3. That's 0.01 liters. So again, what I'm doing right now is I'm figuring out how many moles of H+, are coming from each strong acid. So we have 1 times 10 to the negative 4th moles of HBr, which is equal to moles of H+, because it's a strong acid. So up here, I'll have 1 times 10 to the negative 4th, plus, figure out how many are coming from HCl. So 2.5 times 10 to the negative 3rd molar is X moles over 0.02 liters times 0.02. 5 times 10 to the negative 5th moles of H+ coming from HCl. So we have moles of H+ from HBr. We have moles of H+ from HCl. We add them and divide them by the volume to get the molarity. 1 times 10 to the negative 4th plus 5 times 10 to the negative 5th divided by 0.03. It's 0.005 molar. That's concentration. I mix the two solutions together. Here's the concentration that I get. To find the pH of this strong acid solution, take the negative log of that. .30. So again, for this, we were looking at what's the concentration of H+, that new concentration. Well, we have moles of H+ coming from HBr. We have moles of H+ coming from HCl. This was, out of all of them, right, this is going to be the one that's going to be the most steps. So that's looking at the acids. This question is pretty much identical to 17. So use this as you go through 17. So I want to just look, because I know some people are going to start looking at mastering. This is 18. This is 18. But I want to show you, because as people are working on this, they're already asking questions about the difference between example 8 and example 9, right? So question 17 and 18 of mastering. And I'll have you do some of the calculations just so you can make sure that you're plugging everything in. But just read the question and notice the difference already. Calculate OH minus concentration and pH. Right? Calculate OH minus concentration and pH. And so OH minus concentration means that we're dealing with bases. looking at part A, we have strontium hydroxide. That is a strong base. Get in the habit of labeling everything. Label whether it's a strong acid or a strong base. Because it's a strong base, people miss this question all the time, which is why I put it as an example. When strontium hydroxide is put into water, it dissociates into its ions, but notice the ions that it dissociates into. A strong acid was 1-to-1. Not all bases are 1-to-1. Half of your strong bases have 2 hydroxides. So if this is 3.5 times 10 to the negative 4th molar, notice hydroxide. It's 2 times that. There are twice as many hydroxides. So this is actually 7.0 times 10 to the negative 4th. You have to make sure that you're multiplying. So OH concentration is twice as much as strontium hydroxide. Now to calculate the OH minus concentration, ta-da, there it is. All right, there's the OH minus concentration. So here's part of our answer, equals OH minus concentration. But then the second part is to calculate the pH. Here is where you have got to pay attention to what you're doing. Label everything. You would rather have everything labeled, right, and have too many labels than not enough. Because now, if I take the negative log of this, if I take the negative log of the OH minus concentration, what am I solving for if I'm taking negative log of OH? pOH. pOH. Not pH. You take the negative log of OH, that's pOH. So if I take the negative log of this, right, negative log of 7 times 10 to the negative 4th, negative log of 7e negative 4, the pOH is 3.15. The question asks for pH. Well, remember that pH plus pOH is 14. That's on your equation sheet. So if you have pOH, 14 minus that, which is 10.85, gives us pH. Use the pH scale. All right, use the pH scale to determine if something is acidic or basic. This is greater than 7. Makes sense. It's a base. So for part B, notice part B of 9 is like part B of example 8. We need to figure out the OH minus concentration first. So determine concentration of LiOH. So 1.5 grams. 6.94 plus 16 plus 1.008, 23.948 grams per mole. So 1.5 divided by our molar mass is 0.0626 moles divided by the volume. Make sure it's in liters. 0.250. So 0.0626 divided by 0.25. Divided by 0.25. All right, so 0.251 molar. That's LiOH. Now I like just doing this just to pay attention. There's one OH in LiOH. So this is equal to the concentration of OH minus as well. So there's part of our answer, right? Because part of it wants us to calculate OH minus every time. So then if we take the negative log of that, that's giving us pOH. And then 14 minus that will give us pH. So I'll do this really quick. 0.601. Which gives us 13 point, I guess 3 sig figs, 3 decimals, 399. Again, notice how high the pH is. It's a very high pH. That makes sense. It's a base. Part C, this is another dilution. So we'll just go through part C, and then we'll save part D. So M1V1 equals M2V2. Plug it in. Pay attention to your volume. Are your volume units the same in part C? No, make them the same. I don't care which way you go. You want to make this 2,000 milliliters, make it 2,000 milliliters. But pay attention to your units. I'll do that because I said. So 1 milliliter, M2, I'll use 2,000 milliliters. M2 is 4.75 times 10 to the negative 5th molar of NaOH. There's one hydroxide here, so concentration is the same. There's OH minus. Take the negative log, that's pOH. So negative log of that is giving us pOH, 4.32. Subtract that from 14. Gives us 9.68 for pH. Again, notice how it's over 7. So it makes sense. So we'll save part D. If you want to try part D, you can try it, see what you get. This one's tricky though because of the hydroxides. Right, you're paying attention to hydroxides. And so we have just a couple minutes, but after today you can go through number 19. Remember, if you're stuck on a question, don't guess. Just wait till we go through the example. Video 7.3 is up for tomorrow. It's a little bit longer because it goes through 2 examples. Examples in class, today is like the last long day. Normally it'll be like a period and then a period to work. So just so that you know, I just wanted to try to get through all of these first few review examples that went through mastering. But after today, there'll be more time to work on mastering, to practice. And then any questions as you're working through, right, this